We're seeing a new trend happening in road cycling, and that is people are adopting wider and wider road racing tires. This year at the Tour de France, we saw the winner, the general classification for the entire race was won using 30 or 32 millimeter wide tires. This was literally unheard of just a few years ago. Why do cyclists want to go to wider tires? Well, they claim that wider tires have more comfort, better cornering grip, and lower rolling resistance. Everyone's talking about wider tires. Comfort is not my concern. Many studies have come out recently discussing the advantages of wide tires, but it hasn't come without its controversy. A lot of people still believe that narrow tires at higher pressure are faster. I always say, if you want to get fast, you got to ride with the fast guys. This controversy stems from the fact that wider tires at the same air pressure has lower rolling resistance than narrow tires. Rolling resistance tests were carried out on a rolling drum that verified this fact. Bicycle Rolling Resistance conducted a series of tests in 2019 using 23, 25, 28, 30, and I believe 32 millimeter wide tires, and showed that wider tires, in fact, have lower rolling resistance on the rolling drum. The author of this test, however, pointed out that wider tires at the same air pressure as narrow tires would be less comfortable. This is because wider tires have more air volume, and more air volume makes the tire feel firmer. So the author then repeated the test by establishing a comfort level that all the tires would be equal. And to do this, they lowered the pressure in the wider tire so that the vertical displacement would match that of the narrower tire. And when they repeated this test, lo and behold, the wider tire was the same rolling resistance as the narrow tire. Another test was carried out by fellow cycling YouTuber Cycling About. And he has a website where he publishes technical articles of the things that he's interested in. And one article that he published was looking at the difference between a wide gravel tire and a narrower gravel tire. The wide tire was 50 millimeters wide and the narrow tire was 40 millimeters wide. And in that test, they rode these different tires on a bumpy gravel track, as they said, and they compared the vertical compliance or comfort to each other by using an accelerometer. Now, in order to set the tire pressure in the different tires, they used LaPlace's Law. Now, we're going to talk about what LaPlace's Law is. I'll give you a demonstration. But for now, just know that LaPlace's Law is this idea of setting equal casing tension based on the diameter of the tire. So they used LaPlace's Law to set the tire pressure in this study. And it turns out that the wider tire was in fact more comfortable. Dylan Johnson, who many of you know, fellow YouTuber, current 17th place in the Lifetime Grand Prix, left a public comment on a bike radar video titled, "Are Wider Gravel Tires Faster?" And he makes an argument that the conclusion of the test results in that video would have been clearer if the authors of that video had compared the two tires at equal casing tension. So this got me thinking, does equal casing tension equal comfort? So if both tires, a wide versus a narrow, were set at a pressure so that the casing tensions are equal, does this actually equate to equal comfort? So I looked around on the internet to see if I could find any studies that have been done on this, on bicycle tires. And I couldn't come up with any. So I thought to myself, well, maybe what we should do is set up an experiment and test this for ourselves. I've been racing bikes for 25 years. I run 21 millimeter tires at 120 PSI. That is the subject of this video. Today, what we're going to do is see if we can figure out if wide tires at a lower pressure with equal casing tension to a narrow tire at high pressure will have equal comfort. So what is LaPlace's law? LaPlace's law is a very basic law that discusses pressure vessels. And I'll put up a little diagram on the screen so we all can see what he was saying. Laplace was a famous French mathematician, scientist. He came on the scene about 100 years after Newton was here, and he studied Newtonian physics, and he was really interested in it. He was more noted for his Laplace transform, but he was also noted for the Laplace law dealing with pressure vessels. And basically, to give you a real simple explanation, what Laplace said was that the internal pressure of a pressure vessel, let's say it was a tank like this with a radius, what he said was that if the pressure in the vessel is in equilibrium, the tension or the stresses, the principal stresses in the vessel, that is the stresses in the longitudinal direction and then the stresses in the radial direction, we'll call that R. The radial direction, or the hoop stress direction as it's called sometimes, would be proportional to the size of the pressure vessel. So naturally, a lot of people in the bike world assume that this should also apply to our bicycle tires, because our bicycle tires are thin-walled pressure vessels. And so the formula that comes out of this, if you do the math and you do a free body diagram, the formula that comes out of this is that the pressure in the, or the stress, we'll actually use stress. So the stress in the radial direction is proportional to the width times the pressure divided by 2. So it's essentially a very simple relationship. And if you take this idea and you apply it to a bicycle tire, what you would end up with is you would need to take 2 tires. Well, let's just show it. Let's clear this out a little bit. So if we had 2 bicycle tires, here's a small tire and a large tire. And we'll use a big R for that, big tire, and we'll use a small r. And we have a width of our tire, so width 1, and a width 2. In order to have an equal tension in both of these tires, we would have to vary the pressure. And so according to LaPlace's law, we would set the stresses equal, and we would end up with W1 P1 over 2 equals W2 P2 over 2. And we can rearrange this equation very easily. The 2's cancel. And what we end up with is P1 equals P2 W2 over W1. And so it's a very simple ratio here. We can solve for pressure 1 based on the pressure we put in here. So let's do that, a quick example. And I'm going to pick a tire size. That's the tire size we'll be using in this test, which is a 650, will be a 700C by 25 and a 650B by 48. And we're going to do a test where we run through a series of different pressures and different loads. I'll show you the test setup here in a minute. And we will see if Laplace determines the same load displacement in each of these tires. Will they match? So will the comfort be equal? So the comfort in this case is going to be vertical displacement of the tire. And in order to do that, the theory is that we will set these to equal casing tension, and so therefore the curves will be the same. So here's what Laplace would predict for these tires. So if our width was 25 millimeters, the pressure in the 25 millimeter tire will need to equal the width, or the pressure in the one, so pressure 2 times 48 millimeters divided by 25 millimeters. That's the pressure that we would set in 1 based on pressure 2. Now, if we just assume for now, because I don't have a calculator with me, if we just go to 50 millimeters, then this is simply P2 times 2. So we can see that the pressure in 1, the smaller tire, needs to be twice the pressure in 2. I want you to keep note of that as we do this experiment, we look at the data. That LaPlace's law says that the tension in the sidewalls are equal when the pressure in 1 is equal to 2 times the pressure in 2. Okay? And that makes sense. The skinnier tire will be pumped up higher than the wider tire. Here's Laplace's equation for anyone that's out there and you're interested. Here's a pressure vessel of with 2 different diameters. The pressure in the vessel is all the same, but because the diameter is smaller, the tension in the small diameter sidewall here is low, and the tension in the big diameter is high. So what I have is a very simple setup. This is something pretty much anyone can do at home if they're interested. But I have my bicycle in a bicycle trainer stand with the front wheel mounted in the trainer, and the rear wheel is what is being set up in our test so that we can measure the displacement. And I picked the rear wheel because it was easy to mount that rack on the back of the bike that I could then use as the way to put a hydraulic press on it and push the rear tire down into our load cell. On top of our load cell, we have our dial indicator, which is what we're using to measure the displacement. And I chose to mount it this way because I wanted to take out any possible error that might have occurred if we were measuring it where a lot of tests are done is they're measuring displacement at the axle relative to the ground. And by setting it up that way, you introduce a lot of error in your displacement because when you load a bicycle wheel, the spokes that are in tension relax a bit, so some of the displacement is the spokes themselves plus the distortion of the rim as you have unbalanced tension now in your spokes. The rim itself will also deflect slightly. And the load cell can also deflect a little bit as well. So by putting the measurement from your axle to a point on the ground somewhere, measuring that way will introduce error. I think this method reduces the amount of displacement error as much as possible. We have our dial indicator set up directly over our contact patch, and we have the contact patch sitting on this 2x10 wood block with a circle cut out of it so that we can read our load cell. And why that's there is because this platform on the bathroom scale is made out of very thin metal. And while it worked great with my magnetic base, the problem was the tire puts a concentrated load in the middle of our bathroom scale, and it actually causes the bathroom scale surface to bend, and that threw off the measurements a little bit. So by putting this 2x10 on here, we're able to distribute the stresses more evenly on the load cell and take out that distortion that was happening. So the forces for our load test are being generated by this bottle jack. This is a 4-ton bottle jack, and it is pushing up on this 4x4 post, which is mounted to the ceiling. And I mounted it with these metal angle clips. that keep the post hanging from the ceiling rather than sitting on weighing down the jack and the bicycle and adding weight to our test. So the post is not actually included in the weight that you see here. There's 36 pounds right now, and that's the bicycle, the bottle jack, the 2x10 on the scale, the dial indicator and magnetic base, and this other 2x10 up here, which is just to help level out the bottle jack so that all of the load is collinear with the rear axle and contact patch. I wanted the load to be as straight as possible to reduce any eccentricities or any, I don't know, anomalies that might have occurred, any out of plane loading that might have occurred when we test it. The front of the bike is supported by this bicycle trainer stand, and everything is very solid here. Nothing is moving around when we're loading it. As you can see, if I go ahead and run through a little example here. So this is just to lock in the jack. You can see there's no contact right now between the 4x4 and the bottle jack, so it's free to move around. So let me go ahead and get this thing started here for a second. So we'll go ahead and, as you can see, we're gonna push that, and then as you can see down here, we will get, as I pump this, we can carefully apply load to the tire. And while that is going, you can see that the dial on the dial indicator is also moving as we apply the load. Now this dial indicator here is a 1-inch dial indicator that I've had for a really long time actually. I bought this when I was in high school at Harbor Freight. So this is a 1-inch dial indicator with a graduation. Each one of those points on there is 1/1000th of an inch. And over here, we're accurate to about a pound. Each one of these points on here, each one of these graduations is 1 pound. And we go all the way up to 320 or 330 pounds. But for our test, we're gonna stop at 300 on our scale. I'll be running 2 different size tires using 700C wheels. So we're gonna be using this wheel here when we do our 700C because it's got a very similar style of rim. Not exactly the same width, but fairly close. And I will measure rim width as well as tire width, and I'll report all of that in this experiment. So this is the dial calipers that I'll be using. These are very accurate down to also 1/1000th of an inch. For air pressure, I will be using this floor pump. I actually have 2 floor pumps. I checked the 2 floor pump gauges to each other and they were off by about 8 pounds per square inch. So they're very different. But anyway, we're gonna use this pump for all of our tests and all of our pressures. I do not have one of those special digital tire pressure gauges. I have a old school one that's the sliding gauge, but it has a Schrader valve type valve on it and it won't work with the Presta. I do have a Presta valve adapter, but you know what, for the sake of simplicity, this is the gauge I'm using for my tire pressure. But like all tire pressure gauges, they are not very accurate, but this is consistent as long as we use the same tire pump with tire gauge for all the tests. At least the test data is consistent. Okay, so let's take a look at the data that we collected from this experiment and see if we can figure out what's going on here. So as you can see up here, top left corner, we have a 650B by 48. That's the first data set. And these numbers are related to this 10 psi. So we started off with 10 psi and we went up 10 psi to 20, 30, all the way up to 70 psi for the 48 millimeter wide tire. For the 700 by 25, we started off at 20 psi and we went up to 120 psi. Now, I will point out in this data, we have the measured width of the tire at that pressure. So these numbers here relate to the width of the tire measured with the dial calipers at each of these different tire pressures. So 20 psi, it was 1.855 inches. The load here, this is the column for our loads. These have been corrected for the additional 10 pounds that was on the load cell from the wood block and the dial caliper and stand. So that's why it stops at 290 pounds. And then the displacement numbers are over here in this column, and these are the adjusted displacements based on the adjusted loads. And I created a 0 point with a 0 load just so that the graphs that we're going to look at now start off at more or less 0. So these are the graphs from this data. So all this data for all these tests were plotted together on the same charts here, the same graphs. And I did that so that we could see how each data set compared to the previous data set. So this particular chart is the 650B by 48, and this one next to it is the 700 by 25. And these are all the data points for both tests, for both tires. Now you'll see this data set here stops at about 220 pounds, and that's because the 25 millimeter tire bottomed out at 220 pounds at the 20 psi. So we stopped the test early. Over here for the 650B, we started at 10 psi and we were able to complete the test up to 300 pounds. But you can see it's quite a lot of displacement. Now these lines that are on here, these are an approximate curve fit for the data set, and it's utilizing a polynomial second order equation to predict or to show the trend of the data. So what's nice about this data set is that I have them colored. So red is 650B by 48 and blue is 700 by 25. And what we can do is we can overlay these charts and take a look at the differences in the data and how the two tires will, in a sense, compare to each other. We can clearly see that the 25 millimeter tire has a lot less deflection. And deflection, by the way, is over here on the y-axis. So we're plotting deflection on the y-axis and load on the x-axis for both data sets. We have both axes scaled to match each other here. So when we overlay them like this, we can see how the two tires compare. And what I want you to notice from this data is a couple of things. First, that as the load increases, the displacement it's increasing at a decreasing rate. So it's a non-linear curve. So this is one data set here. This is 10 psi, 20 psi, 30 psi, 40, 50, 60, and 70. And then over here you have 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, and 120. So each line, if you kind of visually study this, you can see that that's one data set for the 30 psi, and then this is the 40, and so on. But what I want you to notice is that the distance or the space between the tires is increasing at an increasing rate, so it's nonlinear, even though the pressure is only being increased by 10 psi. Pressure is being increased linearly, but the displacement is increasing nonlinearly. And also, as load increases, the displacement is nonlinear. So we have a very kind of nonlinear relationship here in this data set, at least from this test. So now what we want to do is see if Laplace would predict a similar load displacement for these tires. So what I've done is I've dug through the data and I looked for the data. So I overlaid these data points like this and I zoomed in and I tried to find the best fitting data where the two curves matched each other as closely as possible. And I could see that this data set, blue and red, kind of overlay really well. This one's pretty close. That one's pretty close also. So down here in these areas here, we're starting to see some similarities. So I went ahead and pulled out a couple of data points where the two charts were overlaying themselves very similarly or very equal. The two tires at these pressures. So here's two data points, and you can see that these two curves match each other pretty well. I have the charts again scaled vertically to be similar or matching, and we can see that blue and red are following nearly the same trend. So what is this air pressure? So let's see. This is the 25 millimeter tire at 60 psi, and this is the 48 millimeter tire at 50 psi. Now, if we were to use the LaPlace pressures, if we use the 60 psi and the 80 psi, or 30 psi, which is what LaPlace would tell us if we use the LaPlace relationship, as you can see, the two curves are not the same. The 25 has much less deflection at every load, so it's not going to deflect as much. So LaPlace, essentially using the LaPlace's law, or setting the casing tension equal, will penalize the narrow tire while giving some slack to the wider tire. Now I chose 30 psi because 30 is a more realistic number that you would run your 650B/48. Most people are not going to run 50 psi. That is just way too high for a 48 millimeter tire. It's going to feel very harsh on the road. But if you were to try and match it with this, if you were to try to find a pressure where the two tires feel the same, you would have to set it to 50 psi and the 25 at 60 psi. There and again, you wouldn't run your 25s at 60 unless you're me and you've now noticed this relationship. I do try to run my 25s and 28s down to 60 psi because I know that it feels a lot better. It is actually a lot closer to how a wider tire will feel. So I just wanted to show that so we can see how the LaPlace equations are going to the LaPlace equations are not going to predict the load displacement correctly, and that's why we shouldn't be using them. Okay, so next we need to figure out, why is this the case? I don't know why you guys can't just shut up and ride. So now that we've had a chance to analyze the test data, why didn't LaPlace's law predict the comfort of the bicycle tires? To answer that question, I think what we need to do first is take a look at the geometry of a bicycle tire and why it may not behave the way LaPlace's law would predict. So a bicycle tire is formed from a geometric shape called a toroid. And a toroid is formed by taking a small circle and sweeping it around a large circle. That is how a toroid is shaped. It's not drawn very well here, but you get the idea. It's essentially, it has two different radiuses. It has the small radius and the large radius that creates it. So it's a donut. And toroids have very interesting geometric properties. One of the things that's really interesting about a toroid is the different cross-sectional shapes you get when you slice it up. So to kind of look at it from the perspective of a bicycle tire, if this is the ground surface here, and we wanted to look at how it might behave when it's pushed on, we can take cross-sectional cuts through the tire and look at each one of these cross sections to see what the shape of the cross-section looks like. And if we take a cross-sectional cut at an equal distance, so if we start at the bottom here at the ground before there's any load on it, that's the very first point of contact with the ground, that cross-sectional cut would look like, in theory, just a point in space, no area, just a dot. And then if we go up some distance here to so this is number 1, if we go up to number 2 and we cut through there, that cross-section is going to begin to look like a circular shape that is basically elliptical in shape. Okay? Then if we go up another one, let's say 3, so this is 1, this is 2. If we go up another equal distance, we will take a look at that cross-section, and again, it is going to look like an elliptical shape. And this is the cross-sectional area number 3. And if we go up another equal distance and we cross, and let's say we picked our lines, our distances perfectly, such that number 4 crosses right at the top of where it starts to curve down to the other side, so right at the top here, right before we go into the void space, that cross-section is really interesting because it looks like an infinity symbol. And if we cut another section just above that, again, equal distance, 4, that cross-section now is going to look something like this. Where these are going to look sort of like elliptical shapes, but more like an egg, where the radius on this side is larger than the radius on the inside. And there's going to be 2. So this is section 5. 1, 2, 3, 4, 5. That's cross-section 5. And then if we just kept going, we'd keep seeing these get further and further apart as we reach the midpoint here. And those would basically just be 2 perfectly round circles. Now, a bicycle tire isn't going to be pushed into the ground all the way down to where we hit the top of the rim with the ground. So our load displacement of our tire is basically going to end here. We're not going to go past this point. But this is really interesting because this helps us see what the contact patches of the tire might look like. And if we remember back to some videos I made a really long time ago, we talked about this and we said that the area of the contact is equal to the force divided by the pressure. And the force is the force acting through the hub, pushing down on the tire, and the pressure is the pressure in the tire, and therefore the contact patch area, that's the cross-sectional area, is proportional to those 2 values. And we can see that this is a linear relationship in that as the force increases and the pressure stays the same, the area goes up linearly. It's a linear relationship. If we look at that, area is going up linearly with the force. And we have a slope of a line there. We have a constant slope. However, if this wheel with this tire being a toroid goes down, it's pushed down into the ground, we can clearly see that these areas appear, at least the way I've drawn them, to be increasing non-linearly. And they are. And how do I know that? Well, like any engineer might do who doesn't have a lot of time to revisit parametric equations of toroids, we do what any engineer might do, and that is we would go to our AutoCAD and we would create this toroid using a small radius and sweeping it around to create this 3-dimensional object. we can define that radius and that radius to create the three-dimensional toroid. And then we can just go ahead and start slicing through it at equal distances, and we can study those cross-sectional areas. And sure enough, we get a non-linearly increasing area, and the area is increasing at some sort of power law. Maybe my test data was wrong. So how do I know? So I decided to look around online to see if I could find any research on load displacement of bicycle tires. And I came across a recent article that was printed or published in 2022. And we're going to take a look at that article and see what they said about how they tested and created their theoretical model for the bicycle tire. So let's take a look at that. This was published by a university out of Girona, Spain. And the authors they did a load displacement test for two different tires, a mountain bike tire and a road bike tire. They wrote up a very complicated parametric equation for how to calculate a theoretical displacement of a toroidal shaped bicycle tire with a truncated, I'll show you the diagram that they came up with. But they truncated a bicycle tire on the wheel, on the rim, and then came up with these equations here to try and theoretically determine the load displacement. So here it is. Here's their theoretical model. You can look at this if you want. I'll put a link in the description. And then they tested it, a real tire, on a load cell like I did. And this is their chart. And as you can see, it looks very similar to the one I came up with. So I found that to be really interesting. I was happy to see the similarity here and that my test data was pretty consistent with their test data. Same curve, shape, more or less. You can see that it's both nonlinear in terms of it at a uniform pressure. If you vary the load, it's nonlinear. And then as you increase the pressure linearly, the difference in deflection is also nonlinear. So it's like a fan. There's this kind of fanning effect that's going on. And this is with the flat plate test as well, just like I did. Okay, so now that you've seen that test and that sort of backs up what I've done, we have pretty good agreement, my test data with the test data that they did, and this idea of the toroid making sense with both my study and their study. So it seems like we can say that the bicycle tire is largely dependent on the shape and diameter for vertical displacement, more so than it depends on the casing tension. As you saw, the author of that article talks about how his model assumed an inextensible membrane. So that basically means that the tire does not stretch under load, even though in reality it does stretch a little bit. It's a very small amount, and we saw in my test data that I measured the increase in width, which only increased a very small amount as we increased the pressure. So that kind of confirms that the tire itself is a very inextensible membrane. Not perfectly inextensible, but pretty close. And so that doesn't affect the way the tire displaces as much as the shape of the toroid does. So it appears, at least for now, that the toroidal shape is more a determining factor for how a bicycle tire will displace than the actual construction of the tire and the stiffness of the tire casing and all that. Cycling is about pain. If you can't handle it, you won't win. So anyway, I thought all of this was a really interesting study. I think there's still more that can be done on this subject. We definitely need to take a look at how the vibration portion of this comes into play with our understanding of bicycle comfort and rolling resistance, but I have yet to see that either. So I'm looking forward to watching this subject continue to evolve. And until then, we'll see you guys in another video. So thanks for sticking around. I hope you enjoyed it. I hope you got a lot out of it. and we'll see you soon.